Thanks for hanging in there. The first half, applause already. So what I was trying to do in the first half was to try to paint a picture of why we should care about stochastic programming, why it's important to think about uncertainty in optimization models. Not only important, I would say even essential in a huge number of applications. And I try to get across that if you account for uncertainty, you're going to get often fundamentally different decisions that I think in a very reasonable way will be better than if you don't account for uncertainty. So what I'm going to do in this second half is get a little bit more technical, talking about on a very high level mostly at the technical components that are important as you get into the business of actually analyzing and solving these type of optimization problems. Of course, as you saw, I alluded to some earlier, there are many, many different types of optimization problems. And same with stochastic optimization models. In fact, of course, since stochastic optimization model is a generalization of the deterministic one, you have an even larger variety of possibilities here. So please don't take what I'm going to talk about here as the only areas of interest. There are many, many possibilities, but I think some of the tools that are at least going to hint towards are applicable quite widely. I'm going to focus a lot of what we call stochastic programs with recourse, and you already seen some examples of that in the first half, both the news vendor as well as the product mix problems. These are stochastic problems with recourse, and that simply means that I'm going to make a decision first, then observe the value of some uncertain parameters, and then we are going to make some adjustments. In the product mix case, it was simply to call up our cousin and ask him to come over and help out as overtime help. Of course, this could be much more general. Okay, so the first story we're going to talk about is simple recourse. And because recourse, not all recourse are created equal, there are different types of recourse, and the simplest one is naturally simple recourse. So in a simple recourse situation, we have exactly what we talked about. We first have a decision, followed by an observation of this unknown parameter, and then we're going to do what I'm going to call a recourse cost evaluation. So that is exactly the situation that happened in say, the news vendor problem. The moment I made a decision about how many newspapers to buy, I've seen demand. There's no fuss about what my recourse is going to be. It's not like this is a complicated process. I will simply just figure out what is the smaller of the demand and my order quantity, and that is indeed going to be how many I'm going to sell. In the product mix case, it was slightly more complicated, but still very trivial in the grand scheme of things. The moment we have decided the excess, how much to produce, we have realized the uncertain parameters. We know how much overtime we need. And of course, with the numbers that I presented at least, there's no reason to acquire more overtime time than we need. So we will simply slide that overtime scale up so we satisfy that capacity constraints that we have. So this is an example of simple recourse. So that is a situation where after we realize the decision, there's a simple evaluation of what the recourse cost is going to be, or recourse revenue is going to be. Okay. We have already talked about these two examples, and here are the mathematical formulas. Say for the product mix case, the recourse function was simply, remember this was the overtime cost, and Tx minus D, that was D was how much I had available of my resources, and this is how much I needed. So of course, if I need more than what I have, I needed to fill in with overtime, and that is done where per unit cost of Q. So whenever this is positive, of course, it kicks in this formula. If it's negative, then we don't need overtime, then it would be 0. Okay. So this is an example where the recourse cost is simply just a sort of an explicit formula we can evaluate. And a similar story for the news vendor problem, where the formula, I guess, for Q will be something like that, where, by the way, I think I made a switch to a minimization problem. I think that's the source of this minus there. Okay. We already seen how these type of optimization problems can be written out in an extensive form. And I think this is for the product mix case. And we have seen already how one can write it as a deterministic equivalent problem. That was a story that there's nothing stochastic about stochastic optimization. That is simply a deterministic optimization problem, of course, involving an expectation. So we end up with something like that. So there's nothing new here. So before I switch, what we're going to talk now a little bit about is analysis of these optimization problems. In particular, things like optimality conditions. I'm going to get in a little bit into the business of algorithm, and I'm going to talk a little bit about duality. So before we get into the business of optimality condition, going to be the first subject, just want to remind you that optimality conditions, of course, in stochastic optimization play as an important role as in other areas of optimization. So, of course, an optimality condition serves the purpose of having a way for us to verify that if I have a particular x, if that x is optimal, or maybe even quantify how far it is from optimality. So to have a relatively manageable way to assess optimality is, of course, a critical step for any algorithm, for instance. If I'm going to have an algorithm, I need to have a way of checking relatively easily for a given x if this x is optimal. But we also know that optimality conditions, say from the deterministic optimization, that optimality condition will also very much inspire more indirectly or directly even algorithms for solving optimization problems. So one shouldn't underestimate the importance of optimality conditions. So let's get into that a little bit, but we'll start with the classical deterministic setting. And as we know, there's nothing stochastic about stochastic optimization. It seems that this should be able to be applied more or less directly to our case as well. But I'll first remind you about the Karush-Kuhn-Tucker conditions. And here stated in the convex case. So if I have an objective function, x is a polyhedral set, and we have some affine function here to define some inequalities and equalities. Of course, we know very well that in this case, we don't even have to worry about constraint qualifications, that if I have an optimal solution, we have an optimal solution of this problem if and only if you have the KKT multiplier satisfy these very familiar conditions. So in a way, if you think about the problem that we have in the stochastic optimization setting, we have something like that. Of course, there's a question about convexity. Do we have convexity in this problem? There will be a question of, for instance, in finding the minimum of the Lagrangian, is the Lagrangian going to be smooth? Can take the derivative of Lagrangian set equal to 0 or things like that. So this will be things that will come in as important. Okay, so let's first talk about the optimality condition for the simple recourse setting. And just remind you of the particular problem that we looked at. We looked at various applications up to now, but let's look at a generic problem. So minimizing Cx, so this is the first stage cost, and then it's the expected recourse cost here. And we have maybe some first stage constraint of this kind. And then the recourse function looks like this, where now I made a small switch on you. Q is actually going to be a function. So Q is not the vector that used to be before. Q is a function of whatever argument is in there. So it could be a little bit more general than what we talked about earlier. Of course, I think when you saw an example where that function was like a max, sum of a max earlier. but let's say it is any finite value convex function. And inside here, you look at the difference between psi and tx. So remember what was the difference between psi and tx? In a way, in the product mix cases, there was exactly how much we need to bring in of overtime. Okay, so we make a comparison between what we need and what we have, in a way. And that is basically what's going to cost us something, is how much adjustment we need to make. So often we find ourselves in a situation that if this argument here is 0, then this recourse cost will simply be 0. Okay. So now my hope is that I'm going to take what they had on the previous slide, these KKT conditions, and simply apply them in this setting. Okay. So what is the challenge that we have now? Well, we have the question of if this is a convex function x, okay? And we're going to return to this, so you're going to take my word for that this is a convex function x. So that's the one thing that is a concern. The other thing is in terms of smoothness. But here you have to ask yourself, is smoothness really something important? And I think in classical teaching, particularly in calculus, smoothness is overrated in the sense that we have a very well-developed theory for subdifferentiation that is going to become very important for us. Because you might remember, for instance, in the product mix case, there was this Q was actually a max function. It was max 0 and something, and then it was summed up. Okay. And of course, the max function has a kink somewhere, so suddenly smoothness is out the window. So we cannot rely on classical calculus, so we need to do something about subdifferentiation. Okay, but the good news is that such calculus is well developed, and I'll talk a little bit more about as we go forward. But if I now want to translate the KKT condition for these problems, at least let's get started and see what we get. First of all, primal feasibility in the KKT conditions is, of course, easily recognized here. So in fact, that's carried directly over from the KKT conditions. So there's no need for changes there. So then, what else is coming in? Well, we're going to look at where the Lagrangian, if it had been smooth, whether the gradient of Lagrange was equal to 0, or more generally, if we have the 0 in the subdifferential of this function here. Okay. And so then it becomes basically an exercise to figure out what is, well, we know how to take the gradient of this first, that's simply C. But the question is about that expectation. So the question is how to compute subdifferentials of this expectation functionals. And I think I have on a later slide actually the formula for it. But basically it is, if you take an integrable selection from the subdifferential of this fellow here. So of course, it must have to do something with the subdifferential of Q with respect to X. You take a integrable selection of these guys, the subdifferential of these guys, and then average those. Then you get the subdifferential of the whole expectation. You think about what we've done in a classical setting. If I feel comfortable with taking the derivative inside the expectation, I will simply take the derivative inside the expectation and take the derivative of Q with respect to X, right? And in a way, I'm just saying a formula that's an extension of that very well-known fact. Okay, so if I do that, so I'm going to take a subdifferential from this Q, and that's exactly what's happening here, except I write out specifically what this capital Q is in terms of little q. So you take, for each scenario xi, I take a subdifferential, and the selection should be an integrable one. And then it's a question of the chain rule, because naturally, there's a tx here, so it will have to be some sort of chain rule that needs to come in at one point or another. So that's why there's a t coming on in front here, and you have the Lagrangian coming out, something like that. So there's like 3 or 4 lines if you want to develop these type of optimality conditions from this condition. okay, so this is all good and well, but let's look at a little bit more complicated situation. If the recourse is not of the simple kind, I said that not all recourses were created equal. The simple one was when you can simply just evaluate the recourse function. So now what if there's something more complicated? Maybe what we call linear recourse. Now we make a decision, we have an observation. And then now, after we observed, it's not like it's simply an evaluation of how much overtime we need, but actually it is a question of finding a y that maybe satisfy a linear system. And that requires a little bit more work to figure out. But say, for instance, in some case where, for instance, we have where W, where's the W showing up here? This W is a fixed matrix. It's not random, okay? Of course, one can imagine a situation where this could be random. But suppose that is not random. And the only thing is random is this D and this T. And again, you can keep the product mix problem in mind. D was the randomness in the capacity of our workshops, and T is the times that these did different things. So this was exactly the situation we had with randomness in the product mix situation, but of course there, this W was like an indicator matrix. So in that case, we were in a simple recourse, but now we're in a situation more complicated with fixed recourse. In this situation, and this is a promise to get back to this business of convexity. So the question is this a convex function X? Well, it might look a little complicated, but the easier way to see it, if you take the, well, at least maybe for the sake of simplicity in this argument, if you think about this objective function is actually a linear function in Y, we can take, for instance, linear programming duality and confirm this minimization problem into a maximization problem, right? And what's going to happen with the right-hand side when you take the dual, linear programming dual, that's going to come up as objective function coefficients. And that's where X is. And I'm interested in properties of this fellow in X. So they're going to be a maximization of something that is linear in X. So indeed, you won't have a piecewise linear function. And the maximum of linear functions, so indeed, we're going to have a convex function. Okay. So that's how this Q can come out as convex. And this, of course, will hold also under more general circumstances. So the long and the short of it is often the deterministic equivalent problem is indeed a convex optimization problem. Okay. So in a way, if you think about it, how much complications have we added when we moved from the deterministic optimization problem to this with, say, fixed recourse? Have we, kind of broken the bank? Is it completely unheard of, much, much harder to solve? Well, say in the product mix case or in any case, we might have started with a linear program, and we now end up with a convex one. And you might say, well, this seems to be an element of complications, but of course, in our business, the big demarcation, by the way, contrary to most other areas of mathematics, is not between linear and nonlinear, it's between convex and non-convex. Okay. So we're still in the business of convex optimization, so in some sense, we haven't made the problem fundamentally more complicated. And by the way, for instance, if we talked about a situation where this little q was not affine, but it could have been a general convex function, we would have started out maybe in the beginning already with a convex optimization problem, and the uncertainty that we have added in, still we have a convex optimization problem. So if you think about, people ask you, well, stochastic programming is so complicated. Well, at least here you have one argument. You can say that, well, often in many classes of problems, we're adding uncertainty remain within the general class of optimization problems. And I can give you many examples where that is the case, that if the deterministic problem is convex, the stochastic, the one accounting for uncertainty, remains convex. Okay, so if you set yourself up right, often that is the situation. Okay. That was what we talked about was in case of fixed recourse. So that was when the recourse matrix, this W is often called the recourse matrix, when that is a deterministic quantity, there's nothing uncertainty about it. Of course, generally speaking, that might not be the case. So you might have a situation with general linear recourse where the randomness psi, there's a randomness maybe in the Q, you know, remember this was the overtime costs. Maybe your cousin, he's a little unpredictable how much he charges for overtime, so there could be uncertainty associated with that. W could be random. T is, by the way, often called the technology matrix. So that was basically the time that it took to make things in the product mix. And by the way, it's called the technology matrix because it kind of, it takes your X to decision X and kind of converts it into whatever you're interested in. So it's sort of a technology that converts your decision into something tangible. And of course, we looked at many situations where this D, this right-hand side, has been random. So maybe all of these are random. So that would be a situation where we talk about general linear recourse. Okay, so now we get to a very interesting and actually somewhat intricate subject. And in a way, this is getting close to the heart of difficulty with these type of optimization models. And that has to do with feasibility. Of course, in the model we talked about, we had a first stage constraint, A is equal to B, X greater than equal to 0. Let's call that K1. These are the constraints that you simply can write down, and it's things that I need to live with when I make my X decision. What is often the situation is that I might actually have additional constraints that are going to be implicit in my model. And let's see if we can explain that. Imagine a situation where my Q, the recourse function, is a simple expression, okay? So here I have a recourse decision that I need to find a Y that actually, I will find the smallest Y actually, it's a scalar. Find the smallest Y that's equal to X minus psi. Remember, X and psi at this point are fixed. X was my first stage decision. Psi has been revealed to us. I'm limited to Y greater than or equal to 0. And what I need to do is I live with the fact that psi is going to be a number between 1 and 2. Okay, so sometimes it's going to be this and that. So if I now look at what x's will be okay here. So if I, for instance, try, I don't know, if I try x equal to 5, right? 5 minus something 1 or 2, so it's certainly still a positive number even if I subtract off 1 or 2 or something like that. So the y that I can have to match it will be whatever that 5 minus, say, 1.5. So I can have a y that matches it. So indeed, I can find a y that works. Okay. And of course, that will, whatever that y that works, that will be the recourse function, the value of the recourse function for this psi and x. But here's the problem. Suppose I selected an x that was 1. Okay. In the first stage, I selected an x was equal to 1. And by the way, what is things that are preventing me from selecting different x's? Well, those are these ax equal to b, x greater than or equal to 0. So maybe simply x equal to 1 was feasible with respect to those constraints. Those dealt with other aspects of my business. And x equal to 1 looked good. Well, now if I look at this formula now I have a little bit of an issue if psi takes on a number greater than 1. So if I have psi again coming in at 1.5, and by the way, I need to consider all numbers between 1 and 2. If it comes in 1.5, then I have 1 minus 1.5. So on the right-hand side there, I have negative 0.5. And of course, I cannot find a single y, non-negative, that will match that. So now I have a situation that in this minimization problem, I cannot find a single y that works. And of course, that is what we interpret conveniently as plus infinity in a minimization problem, right? So this is a situation where we're going to think about the recourse function taking on the value plus infinity. Okay, and of course we can study this a little bit more carefully, and we can figure out that if we look at the domain of this expected function, the expected recourse function, the domain of the expected recourse function is, of course, where the expected recourse function is finite. By the way, we're going to rule out the possibility of minus infinity for the sake of this talk. Of course, minus infinity is something obscure. If I have a decision x, and I somehow can bring this down to minus infinity, there's probably something wrong in the modeling thing. So I'm going to assume that we're dealing with proper functions, meaning that they're not going to be able to go down to minus infinity. Okay. But plus infinity indeed is something that's going to occur, and we just saw an example of that, right? If I was unfortunate enough in this particular case to select an x of 1, indeed there was the possibility of, not only a possibility, it was a significant probability, in fact nearly probability, actually probability 1, that we will have a q that is infinity. And of course, if I take an expectation of infinity, that intuitively, that should be assigned infinity. I'm going to say a little bit more about integral functions a little bit later, but it seems at least that the integral should be infinity. So that would be a situation, that particular x that we talked about, I guess it was x equal to 1, that would be a situation where we don't have a finite expectation. So if I look at all those x's for which we have finite expectation, it seems like in this example that is from 2 and up. And so going from 2 and up, you see that has brought in a new set of constraints that were not possibly captured by x1. Okay, sorry, by k1. Okay, it might never be captured by k1. So this is an important thing that makes these stochastic program models with recourse somewhat fundamentally different than some other optimization models, is that the constraints you might write out explicitly are not the only constraints that are there. There are these hidden constraints that if I have an x for which I cannot do the appropriate recourse, I will basically face with a plus infinity for that x. And that's certainly something that's not competitive, and we can interpret as an infeasibility. And that's what we call an induced constraint. It's sort of a hidden constraint that is brought in because of the recourse. Of course, this is not the only area of optimization where this is going to occur. In fact, if any of you have worked with engineers involved in complicated simulations, for instance, just as a small story, I'm working with some naval architects at MIT, and we want to do some stochastic optimization, and I asked them to run 1,000 runs, so that would be 1,000 different values for psi, 1,000 different psis, and get the performance back. And this is complicated, fluid dynamics, solver, and this and that. And you know, with these things take time. So after 5 cores, they come back after a week, and they say, "Oh, here are the solutions." I'm very happy with themselves. Here are the solutions. But it turns out that only 500 or 1,000 runs ever returned a number. And that is because, well, it could be many reasons, but maybe it could be indeed that you have some sort of induced constraint type of situation, that there are actually, these parameter values that we provided are actually not somehow feasible for these models that are being run. But it was impossible to know that ahead of time. Okay, it's very difficult to know that ahead of time. So whenever you have a situation where you're dealing with function, either like a black box, like a simulation at what I just referred to, or it could be something that is apparently more transparent like here, or some other more complicated minimization, it can be generally hard to identify which x's that would be feasible. Okay. So this will introduce what we call induced constraints. Okay, of course, still, one would like to make a great effort to try to identify what is the set of induced constraints. And we can try to develop various characterizations of these things. And here's one, and this is primarily linear algebra. If we now for a moment fix psi, so imagine psi has been fixed. And if you look at a set of x's for which we can find a y, non-negative, that satisfy this stuff. Okay, so that is kind of like a good case. We didn't have problems with finding. For this psi, we didn't have a problem with finding a y. That can, of course, be written as those x's for which this vector here is an element of the positive hull of W matrix, the recourse matrix. And of course, just remind you what the positive hull is. Of course, if you take the column of this matrix W, and if you take a non-negative weighted sum of these columns, these vectors, you're going to get another vector. And if you look at all those vectors, you can construct in such a manner by looking at non-negative weights. Of course, the convex hull will be similar to the positive hull, except then the weights should not go above 1. Okay. Then one can, and this is linear algebra, one can rewrite this condition in terms of the polar matrix. And I don't know if you maybe some of you might not remember exactly the polar matrix. It's not that important for the sake of the big message here, but the polar matrix has to do with a matrix. Polar matrix of W is a matrix that if you look at the row of that matrix, that will define a set of half spaces that is a minimal set of half spaces that will define this positive hull, okay, of W. So this is well defined, and pretty much from the definition, one will then see that the set that we're talking about here is the one where W star times a vector should be less than or equal to 0. So if that vector, in this case, will be this one, and we just distribute it on both sides, we get this relationship. But the important thing at this point is maybe more than the formula is what is the nature of the formula. So what we see here is that we have some matrix, maybe it was a polar matrix, but we know standard ways to figure out what that is, multiplied by a vector, and all these known things. So this is a bunch of inequalities. So this set K2 psi is the intersection of a bunch of half spaces, right? So the intersection of a finite number of half spaces. And so that means that this K2 psi is a polyhedral set, okay? So that is already a nice characterization that we know it's a polyhedral set. So now immediately, if I'm in the business of finite probability, meaning that I have a finite number of scenarios, so psi can only take on a finite number of possibilities, then if I take, of course, which I'm ultimately interested in is to have satisfied for all the different psi, right? That will give me the K2. So if I take the intersection of across all the different psi's, so if I can just run over in a finite number of psi's, so we know that the intersection of a finite number of polyhedral set is going to be a polyhedral set. So then you see immediately that this set of induced constraint is a polyhedral set if you have a finite number of scenarios. Okay. So this is, remember what was the business we were in? We were in to try to see if we can characterize a little bit better what are these induced constraints. Okay. At least try to understand a little bit, and here is one thing one can say about them. And I think generally, I think it's going to be a closed, I'm going to show you this is going to be a closed convex set. And I think there's also another situation where it actually will be polyhedral, and I think that is in the situation where the technology matrix T is also deterministic. So there's various theorems one can write about these things. Okay, so let's maybe summarize a little bit and add a little bit of a sprinkle on top of this. We talked initially with simple recourse. So we have all these stochastic programming recourse, and they come in different types. So simple recourse was where you can simply evaluate a recourse function very easily. One can talk about a situation where we have complete recourse, and that's what we are set up for to say something about now. So what is complete recourse? That is a situation where simply we don't have to worry about the induced constraints because K2 is simply everything, okay? So that means that for whatever x I make, every decision I make in the first stage, there will always be a y that will get me something in the second stage, okay? So there's no possibility to end up in this unfortunate situation that we had up here, where one could have the possibility of no y being available to us, so we get a recourse function of plus infinity. And of course, you see that following our story here, if maybe an operational characterization could be used in terms of the positive hull of W, in this case with this particular level of uncertainty, or these particular things being random, you see that if you can somehow determine that the positive hull or recourse matrix is the whole world, then again we know that it will not be a problem. We will always have the possibility to find a y that will work. Okay, there's another possibility, of course, is that you might be in a situation where there are indeed x's for which I cannot find a y. So there are induced constraints. So this K2 here is not the whole world, but it's just a subset. But now, you might be either clever or fortunate, and or maybe both, but basically you might be in a situation where K1, the first stage constraints, are sufficiently restrictive. They are a relatively small set, but actually for other secondary reasons, limit your first stage decision. So if you find yourself in a situation where the first stage decisions are restricted by K1, and that set is smaller than K2, then of course I don't have to worry about K2 because I'm going to live anyways within K1. Okay. So any induced constraints, although they are there, they are not active. Right? So that's what we call a relative complete recourse. Okay, so the sum of the story here is that a fundamental difference between deterministic optimization problems and the stochastic optimization problem is that we have this issue of induced constraints, constraints you don't know about. You would have liked to maybe even work hard on it, for instance, by working on trying to identify the positive hull of this matrix and whatever. You maybe even work hard and spend computing time to try to identify this induced constraint. But eventually we come down to the question if it's worth it or this and that. But anyways, you need to deal with it in some way. The fact that you're dealing with a recourse, expected recourse that can be plus infinity. Okay. So let's change topic a little bit. And let's say a few words about expectations. Okay. There's no doubt that these expectations keep on showing up. So we need to make sure that we have a little bit of knowledge, at least, about the mathematical properties of functions that are defined in terms of expectations. And even though you might not want to minimize the expectation, because after all, I argued earlier that there could be other criteria. Maybe you like utility, expected utility. Well, there again, the expectation shows up. Or you might be interested in risk. Well, it turns out that many of the risk measures that we are familiar with, like superquantile risks and many of these other ones, they are indeed can be expressed in terms of expectations. So, okay, so we need to say something about expectations. And it's also important to realize that now we need to deal with functions that are extended real values. So when I put a bar on top of R, that just means that we talk about extended real-valued numbers, meaning that to the real line I've attached plus infinity and minus infinity. Okay. Because clearly plus infinity comes in naturally, for instance, through this induced constraint, or maybe through other constraints as well. Okay. So now we have a small issue, which is something that is, familiar from integration theory already, that if I want to define an integral of a random variable, one had to look at the positive part and the negative part and look at the difference. Okay. So if I truncate here and look at the expectation of the positive part, and then look at the negative part, the expectation of that, classical integration, of course, talks about both of these must be finite, and then we have integrability. But here we don't worry too much about finiteness, actually. It's okay if this one is plus infinity. We just simply say that the integral takes on the value plus infinity. Of course, we have a small issue that we need to resolve, is that if this is plus infinity, and this is also plus infinity, so we get minus plus infinity minus infinity, what should that be interpreted to be? And in many cases in variation analysis, typically infinity minus infinity is typically interpreted as plus infinity, okay? And that seems to make most sense, and that is the convention that will apply here as well. Okay, so we have basically a calculus to deal with this extended real value numbers. Okay, so now let's try to summarize some properties that is important in this context. So we have a function now that depends on two things: xi, think about it as the random parameters, and also x. Okay, they can go into the real and not even real; they can even go into the extender reals. And of course, the reason that we might want to get into the extender reals even at this point, of course, this is before we take the expectation, is that we might even want to capture constraints. And of course, there's the way that the convex analysis works for many, many years is that often one can, in an elegant way, account for constraints by simply assigning plus infinity at points for which you have infeasibility. Okay? So that is a way to build in constraints with at least little notational addition, but also a lot of other simplifications. Okay. So now, if I have the assumption that the integral function is not identical to plus infinity, well, that's important. I'm not ruling out plus infinity, but I'm not saying it should not be plus infinity for every single decision x. Okay? Of course, that's a big difference. I allow plus infinity to some places, and this would correspond to infeasibility being in this or that way induced constraints. But there are some x's for which I actually have a finite number. Okay? So now under this condition, we can show that if I have this lil f is a convex function x for every psi, then the integral function, which of course is a function of x as well, will be convex. And the same story is about affine or sublinear. Everything carries over through the expectation. Lower semi-continuity, it's a same story that lower semi-continuity carries through the expectation function. Okay. What about subdifferential? And this was the rule that I alluded to earlier, and here maybe it's a good time to write it out properly, because it was so central when we developed optimality conditions. So if I want to ever take the derivative of an expectation, but of course, we have the issue of that expectation might very well be a non-smooth function. So we don't kind of simply take the derivative. We need to apply subdifferentials in some way. So here's the formula for subdifferential. So if I have a situation that I'm looking for the subdifferential at a point x, if I have that near that x, that the expected expected value function is indeed finite, so we're in the interior domain of this integral function. And for all psi, we have convexity in x. Then we have the formula that I kind of said earlier, that the expectation, the subdifferential over this expected functional at the point x is simply that we can take subdifferentials, so take subgradients from the subdifferential of the inner function, but make the selection such that it's integrable, and then one simply take the expectation of those subgradients. Okay. And that was exactly what we did to the derivation earlier. Okay, so now maybe we can say a little bit more general optimality condition. The one we had earlier, there we relied on finiteness and things like that, but now basically we are in a position to say a more general optimality condition. So if you're in a situation where I have an expectation functional, and we have convexity, then we have this nice optimality condition, that x naught is optimal for a problem, if and only if something is true, that we can find these subgradients, one for each psi, that should be summable or integrable, so I can compute the expectation of that, should expect equal to 0. And that should, of course, be like, so this is a direct application of the formula that we had on the right side, combined with, of course, Fermat's rule that says that 0 should be in the subdifferential for a sufficient and necessary condition of optimality of a convex function. Okay, if I, this condition here, that we have the subgradient in this subdifferential, of course that is equivalent, because of convexity of this fellow, to saying that this x naught is in the minimization. Of course, the way I thought about this first is, of course, that if I take the derivative, just think about in, say, in the smooth case, take the derivative of this thing with respect to x, what do I get? I get gradient of f minus v, and that is the thing that's going to be equal to 0. And so then it turns out that f is equal to v, and that's exactly what we have up there. The gradient of f, or subgradient for that matter, is roughly speaking equal to v. But okay, so this is nice, and this is not long proof after we have this subdifferential calculus down. It's not much of a proof. But let's focus on one, I think, a remarkable fact. Okay. If you look at this, this is true for each psi. So is there somebody with a clever idea how would I now construct x naught? Keep in mind, x naught is the optimal solution of the problem we're interested in. Okay. X naught is the really thing we're interested in, is the optimal solution of the expectation problem. What it says that I can obtain such x naught by selecting a single psi. You can select a single psi and solve this minimization problem. So if you somehow know v, you can select a single psi, put that in here, and solve this problem for a single scenario. So that shows that I can solve a stochastic program, expectation and minimization, by looking at a single scenario, a single psi, and optimize that. Slightly modified, of course, with this term back here. But in a way, I think this is somewhat of a remarkable fact, but maybe I'm easily impressed. But I think you can solve a stochastic problem by solving for a single scenario. Of course, the caveat is that one has to know what this v is. Okay? So if I somehow know v, I can solve this stochastic program just by looking at one scenario. So basically, knowing this v, which are these subgradients, allow one to interchange kind of minimization expectation. Okay? And of course, when people realize this, of course, there's a lot of thinking that can now come in terms of algorithmic development. As I said, one of the motivations for developing optimality condition is to spur activities into developing good algorithms. And now suddenly we have a new insight that can be used to develop algorithms. And in fact, as we go forward, we're going to make this a little bit more concrete and eventually end up with a progressive hedging algorithm. Actually, we're going to do it right now, I think. So let's elaborate a little bit about this thing about interchange of expectation and minimization. Imagine that you find yourself in, this may be a little unusual situation, but play along, okay? Suppose my decision x is actually not a vector, but is a function of your psi, okay? So basically, in plain language, I'm allowing myself the decision x to depend on uncertainty. So the first stage of decision can depend on uncertainty. So from a practical point of view, this means that I'm applying kind of like a wait and see approach. I'm only going to make a decision at the point when I know psi, okay? Or maybe, thought about it in a little different way, I have all the possible psi listed in front of me, a million scenarios. I'm going to make a contingency plan for each one of them, okay? That's, of course, another possibility. Okay, so if I have that, it's easy to realize under, if this x is permitted, of course, now it's a function of psi, so we live in some sort of function space. But if that function space is sufficiently flexible that I can move up and down x for different psis, maybe, certainly if it's continuous, then there would be not much flexibility. X is continuous with psi. But if I'm flexible, I can move x up and down with xi, more or less at will, then the problem of minimizing, finding an x for all these different xi's is the same as simply carrying out a minimization for each xi and then take the expectation afterwards. You see, has been an exchange of minimization and expectation. And indeed, one have equality here, as I said, if we have sufficiently flexibility in this x, okay? But of course, this is not the exact situation that we find ourselves in. And the main reason is that I am not able to implement a plan that depends on xi, because it's all good to make a list of contingencies. In scenario 1, I want to do this. In scenario 2, I want to do that. But the thing is, I need to make a decision maybe now, before I know the scenario. So what should I do? I have a bunch of contingencies. What should I do? I need one decision at this point. So really what we typically have is a situation that I can, when I have a single x, an x that is constant in xi. So now let's think about how one can somehow trick, using the thinking that we've just been through, so we can somehow trick ourselves back to that situation. So our problem here, I want to find simply an x that is, say, constant. Think about the vector as constant in xi. I can stick with this setup where x depend on xi, which we didn't, is not implementable. But then I can introduce a constraint. I said, okay, I allow myself apparent wiggle room, meaning that for each x xi, I can pick something different. So I have a plan depending on the scenario. But then I impose the thing I would like, backdoor, if you like, by a constraint. That x for each xi should be equal to the average of the x's. And of course, if for each psi, I say that x of psi is equal to the average, that means that x of psi must be a constant. It's a constant function in psi. And that's, of course, that's what we need. I need to have one x that does not depend on the scenario. Okay? And that's something I can implement. And why would I go to this exercise? It seems somewhat silly. First, allow myself flexibility to make a plan for each scenario. And then afterwards, introduce a constraint that tie them back together. Of course, the reason we would like to do that is because now we can start studying Lagrange multipliers associated with these new constraints. Because something that we have an understanding of is what is the effect of constraints in optimization, right? We can say something that through quite powerful tools centered around duality. Okay, so I have now an equality constraint. Okay. So just remind you our setup. We haven't abandoned it, even though I've been kind of a little flaky here and there, but we haven't abandoned the setup that we're going to make a first stage decision, observe randomness, and then we're going to make a second stage decision that is allowed to depend on the realization of the random variable, because we're going to do it after we observe the uncertainty. This is, of course, what we call y earlier, and this is what we call x. And by the way, 2 stage is not the end of the story. I could have continued in any number of stages. So after here, I got a new xi, I learn more. And then there's an x3 maybe that will now be allowed to depend on the first xi as well as the second xi. And the story will go on. Okay. So we are really interested in what to do now, x1, and that shouldn't depend on the uncertainty. So now the question is, and kind of important on a fundamental level, that I think we are in a good position to address now, and that is what is the value of information now? Because if you think about it, if I want to compare the situation where I'm allowed to make a decision now, knowing the scenario, basically it's a wait and see. I'm waiting for the scenario, and I collect information from I know the scenario, and I make a decision tailored to that scenario, versus the situation I've been stuck with now for a while, where we want to make a decision before we know the scenario. So the question is it worth waiting? How much value does we get from waiting? Maybe, of course, in real life, you pull out your wallet and maybe collect more data, so you actually know the uncertainty before you make the decision, right? Maybe through extra surveys or something like that. One can work on the question, what is the price you're willing to pay for such information? And that's, of course, what we'll be able to say now something about as we start talking about this constraint here. What are the Lagrange multipliers associated with this constraint? Okay. So I guess this on a high level, what we're talking about is that a here and now problem can be reduced in some sense to a wait and see problem if you just introduce the appropriate price of information, okay? And in a way, we talked about that earlier, that if I just knew that V earlier, I can solve a stochastic program by just look at the one scenario. Now we're trying to drill a little deeper by looking at when there's particular structure in the setting and how things will come out then. Okay, so here's the problem I like to have in this notation. We have an x1 and x2. x2 depends on xi. We might have constraints on x1. We certainly have constraints on x2 as well. But those constraints might very well depend on xi. After all, those decisions are made after xi has been revealed. Okay. We did a little trick. The trick is that we're going to say that x1 should also depend on xi. That's, of course, the thing that we cannot implement, so somehow we need to bring in the constraint. And here's the constraint that took care of that. So this is just carry over from the previous slide with the structure of these particular constraints that we might have in an application. Okay, so what we're going to do now, we're going to simply, this constraint, we're going to Lagrangianize this constraint in the usual way. We're going to form the Lagrangian function. And there's nothing special about it. We're going to associate this Lagrangian function with some multipliers. The only thing in this particular setting, because if you think about this constraint, it really projects this function onto the set of constant functions. And because of that, one can do some simplifications, so one actually can limit oneself to multipliers that sums to 1, sums to 0, or expectation of 0. Okay, so here's the Lagrangian. Okay. And thanks to the fact we just talked about, is that we can then, when you take this expectation inside, this expectation of this W is 0, so that term will go away. So it is a sort of a small simplification from the Lagrange, compared to the Lagrangian we just write straight out with an equality constraint. Okay. And that gets us to the progressive hedging algorithm. And of course, the story behind the progressive hedging algorithm is that sometime in the mid-80s, Terry Rockefeller and Roger Wetz were in China, and they were stuck at Beijing airport for some delay. And probably because they were putting off some other more urgent jobs, they started discussing technical matters along these lines. And fortunate for us, the delay was quite substantial, many hours. And apparently, during this airport discussion, the progressive hedging came out. A paper came out a few years later. But the only regret I have is that the airlines haven't delayed Wetz and Rockefeller more frequently, because that could have really advanced our field even further. But here's the algorithm, which is basically using this idea that we just talked about, that we're going to initially guess the multipliers. Of course, the whole story here, this goes back, by the way, to the method of multipliers, the classical nonlinear programming. The whole story is to try to figure out the multipliers. Okay, so the Lagrange multipliers we guess initially, of course, we have in this case the situation that we only want them to integrate to 0. So, but that is, of course, not much of a practical help in terms of guessing. Then we will solve this Lagrangian problem that now looks like this. And from that, with that particular guess of the multiplier, the superscript nu just indicate iteration counter. And of course, we are carried with us all the constraints that we have. And what we want to do, we're going to do this for every single scenario. Okay. And this there's no guarantee at this stage that the solution I'm going to get is going to be the same in x1. I don't care too much about x2 at this point because, of course, x2 should and can depend on xi, but at x1 should not. After all, x1 I need to implement before I know xi. So certainly, the fact that I allow that to depend on xi, of course, that was all our trickery about allowing it to depend on xi, is now backfire a little bit to us because when we solve this for each xi, x1 come out different every time, presumably. At least it could, and in practice typically will. So what one will have to do, one will have to adjust the Lagrange multipliers, depending on if you overshot or undershot, and then go back and repeatedly solve again with the new set of Lagrange multipliers. Okay. It's hard to get this algorithm to converge from a theoretical point of view, including. So what one would like to do is to introduce this proximal term, which is regularizing the problem in some sense by having this L2 penalty, which of course make, in many cases makes this into a strictly convex problem. And you can see that life gets a little simpler to show things that this is actually going to converge to what you like. And indeed, the convergence result that they developed is that this method will indeed converge at a linear rate in the convex case to an optimal solution. And of course, optimal solution means that these constraints on the first stage variables have been enforced. So x1 is indeed constant over all xi. So we have an implementable decision. Okay, so x1 can actually be executed. Okay, so the question is, you might have, how should I implement this algorithm? Fortunately, there's been a wonderful implementation of this algorithm by Dave Woodruff and Jean-Paul Watson, quite recently available in Python, which does all of these things for you, including leveraging Pyomo and things like that to make modeling easy. Of course, in terms of making this method efficient, you can imagine there are issues that can happen. This method can sometimes be slow if you select parameters incorrectly. But what really Woodruff and Watson have done is to kind of provide good defaults for these parameters that show that have good performance. One key thing, and this is a good, maybe in a broader story of stochastic programming, this is an important point that one experiences in this progressive hedging method, is that imagine that we have now a bunch of scenarios, say 1 million. What the raw algorithm, as it's stated here, does, it solves one optimization problem for one of those 1 million scenarios. And theoretically, this works. But empirically, it turns out that this is a little slow. So a quick trick that is been implemented in the new implementation, but it was also recognized in the original work by Rockefeller and Wetz, is the issue of partitioning, meaning that one doesn't actually have to look at all the 1 million scenarios individually. One can actually take the first 10, or whatever you will like to do, but you take a partition of the sets of scenarios, maybe the first 10, then the next 10, next 10. So in the problem that you're solving here is not like this, but it's an average of the first 10 scenarios. And 10 scenarios is not that many. I can write out the extensive form that we'll be talking about in the first half. It's still of manageable size because it's just maybe roughly 10 times larger than the original problem. So I can solve that. And it turns out this is a dramatic game changer from a computational point of view to do this type of clustering, if you like, or partitioning of the scenario, not into individual but in groups. And we question how one would do it. It turns out one can have smart things like picking different types of scenarios and this, that, and that can really speed things up. It also goes by the name bundling. One advantage of this progressive hedging method is that it's very parallelizable. Because if you think about it, we have 1 million problems to solve here. But the good news is that you can send it to 1 million different processors if you like. Of course, there's a small issue that there's no reason that each of these solves should finish at the same time. So asynchronous issues that you often have in parallel computing is certainly present here. And the question is how to handle it. I think it's still somewhat of an open issue, but there's fundamental opportunity for doing this in parallel. Another thing that is nice about this progressing hedging algorithm is there's nothing that prevents us from doing many stages. I just told you about 2 stages, but the story is exactly the same for many stages. We just do one solve for one scenario, now a branch of the scenario tree, or maybe a bundle of it if you prefer. This is also, I talked about in the convex case, if I have integer variables, this method also performs very well empirically. And as you can probably figure out if you know about Lagrangian relaxation, it's possible to construct a lower bound through the Lagrangian relaxation. So actually one can provide solution with upper and lower bounds even in the integer case. And they seem to be quite well performed, at least empirically seem to be quite good. Okay, so I'm going to leave the progressing hedging algorithm at this point and talk a little bit, maybe more generally, about approximation in stochastic programming. And there's no doubt that one of the main challenges in stochastic optimization is the fact that we have an expectation. And unless this expectation is over a finite probability space, and probably finite means low, we have some issue with evaluate this expectation. It will be generally a multi-dimensional integral, maybe very, very high-dimensional integral. So there's no doubt that we need to get into the business of approximating stochastic optimization problems. What we talked up to now, we haven't really addressed that. We say we're going to solve the problem, okay, the whole problem, maybe write out the whole extensive form and solve it as one gigantic optimization problem. Or we're going to use the progressive hedging algorithm, which again solve the problem. But of course, I should stress that the progressive hedging algorithm deals with the situation with a finite number of scenarios. And presumably, from a practical point of view, it cannot be extremely large. So what can we do, or how should we think about situations where we need to introduce approximations? And primarily approximation due to the expectation. And this is something that is applicable more broadly in life. Okay, so when we want to introduce approximation one way or another, some of these things will carry over. So what we have an objective function. We have some feasible region S, is illustrated here. And one way to think about this, and we already alluded to that, is that think about x's outside the feasible region as assigning plus infinity to the objective function. So we simply have a new function f without the not that is extended real value, meaning it takes some plus infinity in the infeasible region. Okay? This is nice for notational purposes and things like that, and certainly in analysis is quite convenient. Okay, the key thing to look at here is the epigraph of such functions. You know, epigraph is everything that your child will color in above that line as you go up. And the level set is those x's for which the function is less than or equal to a particular threshold, say alpha. Okay, so if I'm going to say something now about approximation in the business of optimization, certainly one thing that I would like to ensure, that if I have a good approximation, it should be one that an approximate solution, an approximate optimal solution of this approximation, indeed will approximate very well, or at least reasonably well, an optimal solution of the original problem. So we like to have somehow that the approximate problems indeed generate approximate solutions of the original problem. And you might say, well, this is going to happen anyways. Well, let's look at some examples where that might not be as nice as you like. For instance, if you have a situation that I have a function f nu that I think approximates f, okay? And like always with function, there could be many notions of approximations of functions. So one way would be the notion of pointwise approximation or pointwise convergence. And if I look at this f nu compared to this f, by the way, this f nu is somewhat of a silly function. It's constant, except at a point 1 over nu, for which it's 0. And then it jumps up again and continues, while the function f is just that continuous. So if I look at for any x, you see that indeed you're going to have pointwise convergence of f nu, because any little bump you have in the road here, it passes away, right? So at any x, eventually, well, most of the time, in fact, f nu and f will be identical. So this is a situation where pointwise convergence. But the question is this pointwise convergence indeed getting what we would like to get? And if you're in the business of optimization, it seems like one of the prime things we would like to ensure that optimal solution somehow converges, as I alluded to earlier, as well as optimal values, okay? Optimal objective function values. So look at the situation here. If I look at the optimal objective function value here of the f, we can think about the true problem, and f nu, the objective function value optimal is up here, and in this case is down here. So for whichever nu I have, presumably refining precision, the optimal objective function value of the truth is up here, and the optimal objective function of the approximation is down here. And this is for all nu. There's no notion of convergence, okay? So pointwise convergence in this picture is not sufficient, is clear, and we can construct many other examples where pointwise convergence is basically simply not the thing we would like if I want to deal with optimization problems. Well, we can talk also about the business of uniform convergence. Indeed, if I have uniform convergence, we are going to get convergence of minimizers, we're going to get convergence of optimal objective function values. But the problem with uniform convergence is that we have a fundamental issue when the feasible region also is approximated. So maybe the approximate problem has a feasible region that's something like that, but the truth is over here. So it moved a little bit, so the feasible region moves. And of course, approximation in constraint is just as prevalent as approximation in the objective function. And if you have this type of thing, you're going to find yourself in a uniform convergence setting to compare function values that are plus infinity with some finite number. And of course, that would be plus infinity, so the uniform distance between these two functions, say f nu and f, would be plus infinity, okay? So I will be unable to show that indeed I have convergence in the uniform sense for these functions. So there's a need for some other notion of convergence, some other notions of approximation of functions that are tailored particular to optimization problems. And that notion is epiconvergence. So what is epiconvergence? Epiconvergence is if I use a little e here, so a function f nu epiconverges to f. If for every point I have these two conditions. For every sequence, I have some sort of a lim-inf conditions, and for every, not for every, but for some sequence, I have some sort of lim-sup condition. Okay. And we might say, well, how do these formulas compare, say, to the pointwise case? What is pointwise convergence? Is that you fix x, and you want to check this for every x, and you look at the lim-inf should be greater, and the lim should be less than or equal to. Of course, that means that the limit indeed exists, and it gets to f of x. So the difference from here and up here is that here we look at a fixed x, while here we look at moving x's. Okay. And with regard to uniform convergence, I'm going to state this in terms of continuous convergence. Continuous convergence essentially, at least for the sake of this talk, same as uniform convergence. So what does that mean? That means that if I'm coming into a point, the lim-inf should be greater than the lim-sup should be less than or equal to for any sequence coming in. And that starts looking similar to what's up here, but here you see that this is less stringent, because here I only have to have one sequence doing the job on the lim-sup side, but all on the lim-inf. So it's easier to show this than this one. So in a way, you can think about epiconvergence, some sort of a one-sided uniform convergence, because we don't have to do this on both sides. We do it on the lim-inf side, but on the lim-sup side, it's sufficient to do it for one sequence. Okay. So that's what you think about epiconvergence as sort of a one-sided convergence. Okay. So the question is, what are the consequences of epiconvergence and why it's getting the things we would like to have? So just a little bit notation to make things more economical as we go forward. Let's call the set of arguments of the approximate problem A new, and of the actual problem A. And of course, there might be epsilons involved. We can do epsilon optimal if you like, and we're going to write like that. So we're going to say that we have a V convergence of these sets. Oh, by the way, of course, arguments can very well be not a singleton. It could be a set of optimal solution. In fact, that's typically the case in application that the set of optimal solution might be rather large, in fact, even unbounded in many cases. So if I have such a V convergence, what is that? So this is a definition. That means that if I have a cluster point of approximate, of optimal solution of the approximate problem, I call those X nu. So X nu are optimal solution of approximate problems. If those X nus have an accumulation, that accumulation must be an optimal solution of the actual problem. So they converge to the solution of the actual problem. But not only that, I'm going to have that every optimal solution of the actual problem can somehow be approximated, meaning that there exists a sequence of epsilon coming down, that if I look at the epsilon argument of the approximate problem, they are somehow coming in towards that optimal solution of the actual problem. Okay. And of course, I'm setting myself up for success. Epiconvergence is indeed achieving this, okay? So if I have epiconvergence, I will indeed have these two properties, okay? And we're working a little harder. For instance, if I have a unique minimizer at the actual problem, it's somewhat of a special case, but worthwhile discussing, then it turns out that the whole set of epsilon optimal solutions of the approximate problem converges into that singleton, okay? So that whole set of epsilon optimal, and it does that for any epsilon nu that tends to 0. So that means that in this case, for instance, you can solve the approximate problem even approximately, and you still have convergence in towards the optimal solution of the actual problem. Okay. How are we doing with time? How many minutes? 10 minutes? 5? Okay. Okay, so let's see what we can say. Expectation functionals, we already talked a little bit about this. I'm going to skip this slide then. And basically work in towards a particular type of approximation that are prevalent in stochastic programming, and that's, of course, approximation due to sampling. Any statistician, if you see an expectation and there's a need for approximation or estimation of the expectation, of course, one would rely on sampling. Okay, this is the most natural thing to do. Okay, so the same thing here. I have an expectation that is in my objective function or in the constraint, wherever it is. It could be very natural, if I have the distribution of xi, to sample from that distribution and somehow construct a sample average approximation. So what I'm going to work towards, I think that will maybe be my last 5 minutes. I work towards what could be a justification for such a sampling approach. You might say, well, do I need any justification? But wouldn't classical statistics provide all of this? Well, of course, classical statistics will say things that almost surely the sample average of IID random variables will converge to the true expectation of one of those random variables. But the thing is, we're not dealing with random variables at this point. We're dealing with something that's a little bit more complicated. We're dealing with random lower semi-continuous functions. Okay. So, of course, a random variable it's a mapping from a probability space into the reals, right? Now we're talking about a mapping from the probability space into some function space, the space of lower semi-continuous functions. So every realization of this random element is a lower semi-continuous function. So the question is about what can we say about these random lower semi-continuous functions, and what are the assumptions that we need to bring on board. By the way, a random lower semi-continuous function also goes by the name normal integrands, so that's the same thing, so there's no confusion. Normal integrands are the same as random lower semi-continuous functions. So what is such a thing? Well, I have a function now. It depends on Xi. Think about those as the random parameters, but it could be any probability space. And it also depends on a decision that lives in E. Think about that as that could be our X that we talked about, but it can be also more general. And this is important because remember, we did this trick that we didn't only let X be a vector, but also be an X could be a function of the randomness, and that was very, very handy to get up to the progressive hedging algorithm. So the fact that we allow X to be dependent on Xi, that says that E might not only be Rn, but it can also be some space of function defined on Xi. Say some LP space on Xi, for instance. Okay. So what do we have, or what would you like to have for a random lower semi-continuous function? Well, for every Xi, we want to have this f to be lower semi-continuous than x. And it's important that we permit extended real values. So certainly, if I have a constraint, it's all baked in here. I'm allowed to have this f coming from some objective cost, maybe, and then I add plus infinity when I'm not feasible and 0 when I'm feasible, okay? So even though you don't see constraints, don't go out the door and say this is not relevant. Well, the constraints are baked into this random lower semi-continuous function. And then, of course, we need some measurability assumption. So what I'm talking about when I talk about sample average approximation is, of course, what we have written here. Imagine that I have a sample of size nu drawn from Xi. Okay? So I have, say, IID or something like that, the different Xi's that I've drawn. I can construct the average for that. Of course, this is still a function of x, right? Because x is at play. And I might very well have this when x is, say, feasible for that particular draw. Remember, the draw could indeed depend also on, the feasible set can also depend on the draw. And I can assign it to plus infinity otherwise. And this E nu, I just think about the expectation with respect to the empirical measure. Okay, so now, of course, the fundamental question to us is, does this function, that the sample average is a function of x, does it epiconverge to the true expectation functional? Of course, if it does, in a way, we can rest in some sense, because then we know at least we have convergence. Of course, there's still open question about rates of convergence, a lot of important questions, but at least we know we have some sort of consistency in a statistical sense. Okay. And of course, a statistician will say that what we're working on is a law of large numbers if we want to show this happen almost surely. A strong law of large number. Okay. And here is one result, and this is, I think, the place to access this. If you look at a paper in the mid-90s of Arstein and Wetz, I think that is the latest iteration, at least I can think of top of my head, of this type of law of large numbers. And important thing, maybe for you at this point, is what are the assumptions that need to go into this for me to be able to justify sample average approximations, okay? The sample average approximation is used, while the question is, what do I need to show to be able to justify sample average approximations? Well, I need to make sure that my function is a random lower semi-continuous function. Remember what that is? That was simply that in x, it must be lower semi-continuous, meaning that I'm allowed very well to incorporate constraints that can even be random. Okay? Only to make sure that that constraint set is a closed set. And then I had a measurability assumption that was baked in here. I think for most practical assumption, I will not worry too much about that. That's usually satisfied. And then I need some sort of integrability, okay? And I'll get back to that in a second. If you have that type of integrability, if you have IID samples, and even pairwise IID will suffice. And even one can go back, there's a paper with Korfer and Wetz, which deals with not IID, dealing with ergodic processes. So we can even go beyond IID and get similar results. then indeed we get here what we were looking for, with that the sample average approximation epi-converges to the expectation functional. So we get all these good things that we're hoping for in terms of convergence of optimal, the convergence of the solution of the sample average approximations indeed takes place as sample size grows. And it happens almost surely. So I think the only thing maybe I can end with is what is that integrability conditions? Is it very stringent or this and that? And you might already be a little, get a little cold feet about it because, of course, we have extended real valueness. So certainly, there's very well real possibilities that this, both of these left and right-hand side here, both the sample average as well as the true expectation might very well be plus infinity due to constraints. So when we talk about integrability, it sounds like maybe we are trouble on the horizon. But actually, it's not, we don't need to have integrability in the classical sense. It's a much, much weaker, and it's only on the one side. So what it means specifically, if for every x, so it's a local property, for every x, I need to be able to find a delta so I can make a little ball around that x. If I minimize my function, on that little ball, okay, and whatever number I get, I take the expectation. That expectation should not be minus infinity. Plus infinity is okay, but it should not be minus infinity. And of course, if I'm in a situation where this f here is uniformly bounded below, of course, this would be satisfied. But also if it's just locally bounded below, okay, for every x, we have such a ball. Okay, so I think if Claudia says that this is good enough, I consider my day over. And there will be a little bit more about duality. It's a very interesting subject, but I'm going to save that for some other occasion.
Okay, Claudia says it's very good enough.